Okay, so let's get started. We were discussing last time a deterministic algorithm for the selection problem. And the algorithm was very nicely captured either in a text form on this slide, or by going and looking at this figure, which actually explains what's going on, I believe, pretty well. So what is the basic idea? The basic idea is the following. Unlike this figure, I'm going to assume that n, the number of elements going into a recursive call of the algorithm, is divisible by 5. So this excludes the possibility of these 3 elements right here. So what we do, we take the elements, we partition them into groups of 5. 5, 5, 5, 5. So far, just elements without any order between them. So this is the first step. The second step is that within each group of 5, we find the median of the 5 elements. Now, this implies the arrows going here for here, because we determine, by determining the middle, that the element that exactly in the third location, meaning 2 elements are smaller and 2 are larger, we put them, the ones which are larger below, the ones which are smaller above, and the arrows represent the larger than or equal relationship. So these 2 elements are larger than this guy, and this guy is larger than these 2. Okay. So far, the only thing that we did is internal to each group of 5, we found the median. The next thing that we do is that we call recursively the algorithm. Remember, this is a selection algorithm. So you give it n elements, you say, I want you to find the i's largest. In particular, the i's largest can be the median. So we tell it now, find the median of medians. And now what we have, we take all the guys that were, all the guys in white here, the white slots that represent the median, medians of respective groups. And what we do now is we take the median of median, because supposedly we found it using recursion, we put it in the middle column. And now half the elements are half of the groups of 5 are to the right, half to the groups of 5 are to the left. And the relationship now of the arrows going sideways is also has the same semantics, meaning that all the elements that go to the median of medians are from larger medians, and all the elements from this median of median to the left are to smaller medians. So we permute all the groups in such a way that all the medians that are larger than the median of medians, denoted by X here, are to the right. And for that reason, their arrows go to the left. And then all the groups whose medians is smaller than the median of medians are to the left. And for that reason, these arrows go to the left. Okay, so now comes the big theorem. The big theorem, which we started explaining its proof before actually stating the theorem, is that the observation that all the elements in this quartile are larger than the median of medians. Why is that? Because every element here is larger than its median, and its median is larger than the median of medians. So by transitivity, all the elements in this area are larger than the median of medians. In a completely analogous fashion, all the elements in this quartile are guaranteed to be smaller than the median of medians. Why? Because take the median of medians and compare it to this element. The median of median is larger than this, and the median of this group is larger than any of the elements above. So we have a completely symmetric situation where the median of median is guaranteed to be less than or equal the elements in the lower, smaller than the elements in the lower right quartile, and larger than or equal all the elements in the upper left quartile. So this actually gives us something that we worked hard to get here, but if you remember the randomized algorithm, we just picked an element in random, and somehow over time we were guaranteed to have pretty good choices, because given that it was randomized, we are unlikely to always pick an element in the extreme. Here we are in a much better state because we are guaranteed to be smaller. The median of median is smaller than a fraction of the elements and larger than another fraction. And the question that we discussed is what fraction? And the answer is the following. Look at how many elements are guaranteed to be in this quartile. Actually, it's more than a quartile. I'm going to explain in a minute why. So look at how many elements I have here. We have really groups of 5. And for each of the groups of 5, the 3 lowest elements out of the 5 are where I want them to be. So 3 out of this, 3 out of this, 3 out of this are all larger than the median of medians. But how many elements do I have here altogether? The answer is that I'm excluding at most half of the columns. So I have 3 over 5 from the group of 5 which are included, but the groups of 5 which are included are exactly half. So I have 3 over 5 divided by 2, which means 3/10 of the elements are guaranteed to be larger than or equal the median of medians. If you have a question about this critical point, please please ask now. So let me repeat the claim. The claim is that the median of median is guaranteed to be less than or equal to 3/10 of the elements. And in the same symmetric way, it is guaranteed to be larger than 3/10 of these elements. What we don't know is the relationship to the elements in the lower left side or in the upper right side. And this I explained in the last lecture. If you want me to re-explain it, I'll be glad to do it. But this is the claim. So, so that's really the heart of the claim about the quality of the median of which is guaranteed by this algorithm and was not guaranteed in the randomized algorithm, and why this is going to be a deterministic algorithm. So what is now the observation? The observation is that the last step, which I have not yet shared with you because it is completely identical to the randomized algorithm, is that now we go and rank the median of median relative to all the elements. We are guaranteed that the rank will be higher than or equal 3/10 of the range of n, and it will be less than or equal another group of 3/10. So it will be in the middle of 4/10. Because 3/10 are smaller, 3/10 are larger, so the middle part remains of size of 4/10. So once we rank it, we complete it exactly as before, by taking our I and ask, is I larger, equal, or smaller to the rank of X? And based on that, we split and continue. We either conclude that we found our I, which is the rank that we are looking for, or that it is in the elements which are lower than X, or among the elements larger than X. So this part of ranking X, and then, which is our pivot in this deterministic version, and it's and how to continue from there is basically identical to the randomized algorithm. Again, if you have questions about that, please raise your hand now, because the only thing that remains to be done is to go over the analysis. So is the algorithm clear, and why and how the pivot selection are they clear here? Because that's the main innovation. Okay, so since I don't hear any questions, I'm going to continue here. And let's see. So no questions. Okay. So I'm going now to proceed to the analysis. The analysis is actually quite simple. So I'm going to actually simplify the analysis by abstracting some of the constants that appear here on the side. So jump forward the analysis. What I'm actually claiming is that we can upper bound the time by the following, and I'm going to throw out some junk. I hope it will be clear. Because remember that I'm making here a simplifying assumption that the slides do not make, that n is divisible by 5. Okay, so this is going to make my life easy. And how to overcome where n is not divisible by 5, this is exactly what the slides handle. But at the present time, my interest in this lecture is to abstract away some noise and focus on the essence of the case. So the essence of the case is the following. In order to solve a problem of size n, if n is sufficiently small, and in this draft, in these slides, we picked n sub 0, which is less than 140, an arbitrary number, which, you know, if you analyze the exact quantities here will make sense, but we don't need to do it here because that's the typical asymptotic claim that we only make a case of beyond a certain, in asymptotic land where n is larger than some n sub 0. Okay, so, and then I need to solve a problem of size n. So how do I need to solve it? So the one thing that I need to do is I need to apply the algorithm outside the recursive calls. And what I want you to remember is that in the algorithm that you see both here and here, actually had 2 recursive calls for a selection algorithm. Why do I claim that we have 2 recursive calls? One was a problem of size n over 5. I hope that this is clear, because when we tried to find the median of medians, here my n was n over 5 of the original n, because 1 of every 5 elements participates. Okay, so we have a problem of size n over 5 that we need to do, and this problem of size n over 5 is written here. The other thing that we need to do is, in the worst case, because we throw out 3/10 of the problem size, because we are guaranteed that the element that we rank is in the middle 4/10, and 3/10 of the elements must be larger and 3/10 smaller, we we know that we will get rid of at least 3/10 of the elements. So how many elements will continue in the algorithm? No more than t of 7/10 times n. And why do we have this big O of n? Because all the operations that we do here outside recursive calls, the arrangement, the ranking of the element, the exclusion, and everything that we do outside the recursive calls is no more than a linear number of operations. So if you try to sum up the recursive call that we have, you throw out all the junk, all the constants and all of this, what we have is t of n equals to t of n over 5 plus t of 7 n over 10 plus constant times n. Okay, that's the recursion. And the recursion is written here, again, throwing out these constant factors. So we have c times, okay, yeah, let me please hold this back. So now, what I would like to argue, and now what is my challenge? My challenge is you give me this recursive inequality. T of n is at most t of n over 5 plus t of 7 n over 10 plus big O of n. Now we need to solve this recursion. And how are we going to solve it? We are going to use the same trick or the same methodology that you learned in calculus, where we are going to assume inductively for some constant c that t of n is going to be upper bounded by c times n for all n which are larger than some n sub 0, which we are going to assume here is 140. And now the question is, why will I be able to assume this inductively and prove this by induction? The answer is actually very, very simple. It is because if you add 1/5 to 7/10, what do you get? You get 9/10. And why is this good news? Because 9/10 is a constant fraction smaller than 1. And to the extent that we get a reduction, we are in business. So this actually, this is the whole trick. So the fact that we were able to recursively continue with two problems where where both of their sizes are constant fraction below 1, this type of reasoning of arguing inductively that t of n is at most c times n for some constant n and for all n larger than some n sub 0 will be able to push it through. And that's the whole idea. So I think that with this, I'm basically done with this deterministic algorithm. And this gives you your last opportunity to ask questions on this chapter before I'm moving on. Any questions? Any questions? So I'm stopping share here. And actually, I'd see nobody here today is on video. So would you mind turning on some videos just to make me feel that I'm not talking to some spirits? Yeah, thank you, Charles. Anybody else, just to make me feel better? Okay. So you have any questions? That's the opportunity to ask. Okay. So Okay, so I don't hear any questions. And given that I don't hear any questions, I'm going to proceed now to the next chapter, which I already uploaded to Elms. And the chapter I'm going to upload is this one. It is chapter 6. And a second. Okay. So let's try and see what we can say about it. So this is chapter 6. Okay, so let's try and proceed with that. Second. Okay, so heap sort. So in part, I'm going to start with a motivation similar to the motivation I gave you before for insertion sort. You remember that I challenged you to tell me why, by enhancing insertion sort using binary search to an array. Remember that in insertion sort, we are getting the cards and we move them serially into their location, and then we shift everybody once we found the location of the new card. And we keep doing it again and again. And then I told you why to do it in this dumb way. Why not to do binary search and in logarithmic number of steps, find the location for a card. And the question is, why not to do that and why it didn't work? And to remind you, the problem with that was that the reason it didn't work is because we needed to shift every item to its location, because the binary search assumes that the input for every iteration is given in an array. And in order to achieve this shift, we needed to do the linear amount of work in the worst case per iteration, even if we rank things in logarithmic time. And the question is, how, so it doesn't work, and the question is how to get around it. So that's the point being made here. And my suggestion is that we are going to review several alternative approaches to sorting, which will end up running in n log n time rather than in n squared time, which is the worst case complexity for insertion sort. So it will end up running in n log n time. And what you will see as a common thread among these approaches is that we are trying to bypass the problem of insertion sort. Why in insertion sort we didn't succeed? And using some ideas, we'll see how some different ideas. We'll see how we bypass this problem. Okay, so so I'm going now to describe the notion of a heap and heap sort, and after we do that, we will see how a sorting approach falls into place. Okay, so basically, what is a heap? A heap is a nearly binary search of n nodes. And I'm going to explain that. So for that, I'm going to shift. So what I'm trying to explain now is the term nearly binary search of n nodes, counting the internal nodes of the tree, not only leaves. Okay, so that's what I'm trying to explain. And here is the explanation. So when we look into this figure, what we see here is, I would like to demonstrate the concept of a nearly binary tree, nearly complete binary tree. And for that, what I ask you to do is the following. Ignore for now all the contents. Just ignore the 16, 14, 2, 4, 1, and so on. The only thing I want you to consider here is the numbering of the nodes, 1, 2, 3, 4, up to 10. And here we have an array. And again, I want you to ignore completely the content of the array, 16, 14, 10, up to 1. Just ignore it. What I want you to note here is just the numbers 1 to 10, the indices of the entries of this array. Because as we are going to see, the notion of a max heap, which I'm yet to define, has really two sides to it. One, which I would call syntactic, and the other is semantic. The syntactic is the structure or the framework, and the semantics will bring in the values that you see inside, which I now ask you to completely ignore. So what we see here is a nearly binary search of 10 nodes. So what does it mean, nearly complete binary, I apologize, nearly complete binary tree, not binary search, nearly complete binary tree. So what is a complete binary tree? A complete binary tree is a tree which you have a root, 2 children, 4 grandchildren, 8 great-grandchildren, and so on. So it's always full, where every layer has the power of 2, which matches its designated size. But a nearly complete binary tree means that you give me a certain number, whatever the number is. In this case, it's a 10. 10 is the number of nodes that you want. So what is a nearly binary search? It means, as you may remember, we have here basically a situation of a geometric sum. 1 node at the top, 2 at this level, 4 at this level, and so on. So if I were to have a complete binary tree, its total number of nodes, if you give me a binary tree of size h, it will be a power of 2 minus 1. Just to remind you, if I give you 1, it's 2 minus 1. If I give you 3, you get 3, which is 4 minus 1. If I ask you for 7 nodes, you will give me this, which is 8 minus 1. And if I were to fill this up, you will get 15, which is 2 to the 4, or 16 minus 1. But since the only thing I want from you is 10 nodes, there is nowhere where you can fill it up to make it a complete binary tree. So what is the next best? The next best is to fill up as many layers as you can, and then remain with one layer where you start filling it up from the left and stop where you're out of nodes. So this is the concept of a nearly complete binary tree. Okay, now this explains the concept of a nearly complete binary tree. Now, the one thing I wanted to point out is how you can elegantly and compactly save such tree in the computer. Because in a computer, the computer doesn't know anything about trees. But arrays is a very compact and efficient way of storing information. So observe the elegant connection between the indices here and the indices here. What is the idea? The idea is that in location 1 in the array, we store the root. The root has two children, a left child and a right child. The left child will be in location 2, the right child in location 3. I'm going to soon show you the rule. Now you give me, you want to include more nodes. So node number 2 will have two children, which will be marked 4 and 5. And node 3 will have two children marked 6 and 7, a left and a right. Okay, so far, I haven't yet pointed out the punchline. The punchline is that if you give me the index, I can now, the index of a node, I can figure out its left and right child by doing the following simple thing. If I'm an I, my left child is 2I. If I'm a node I, my right child is 2I plus 1, in location 2I plus 1. So let's confirm that this is the case. Take node 3. Node 3, its index, the index for its right child, for its left child will be take I multiply by 2, and here you find the left child. And indeed, this allows me to map this array directly to the tree. So I can use a tree, a one-dimensional array, to represent this seemingly two-dimensional tree. Let me repeat. Look at the node here, node 3, node whatever. I can, by just looking at its index, I can figure out where its left and right children are in the array. So if you give me only the array, it's as if you gave me this tree. Now, you can also go in the reverse direction. If you are a node somewhere here, say node 9, where is my parent? The answer, take my index, which is 9, divide by 2, which would be 4.5, and take the floor, which is 4. So where is the parent of, of node 9? It's in location 4. And this is this link down there, and it is written right here. Okay, so I hope that this fully clarifies it fully clarifies, I hope, the semantics, I apologize, the syntax of this structure. Any questions about that? And observe that so far I have not said even a single word about the content. I only explained the term, I only explained the heap as a nearly binary tree. Okay. Now, the next thing that I'm going to discuss is, because we are in a computer science and engineering class, we do not care about trees or arrays unless they represent something. And here we would like to come up with a notion of a heap, and in particular max heap, where we will be able to store in each of these locations some value, and there will be some relationship that we are going to see will play a role in order to give us things that we like. In particular, it will at the end lead to a sorting algorithm, which will be an n log n algorithm. Okay. So the property that we are going to discuss, and now we move to the semantic side, is called max heap. So what is a max heap property? It is that if you have a node and a parent, the value written in the parent must be larger than equal the value at the node. So as you go up the tree, the values are non-decreasing, or increasing, if you will. They are non-decreasing. So for example, what you see here, if you look at the content, you see that if you go up the tree from 2 to 8 to 14 to 16, or from 4 to 8, etc., you keep going to higher and higher values. So each pairwise relationship is between an element and a parent which has a larger value. And for that reason, the max heap property is satisfied here. I hope that this is clear. And I'm going to explain down the road why what I'm sneaking on you here is a much richer concept than just a binary tree and its representation of the max heap property. I'm sneaking on you a completely new concept which is known as data structures. And just remember that I need to, what I owe you is to explain what are data structures and so on. And in what way from algorithms. So what is an algorithm? An algorithm, as we demonstrated so far, is given a certain input, and at least what an algorithm should do is produce some output. And an algorithm is correct if you have a problem definition, which includes an input and an output. So the problem definition is clear here. And the algorithm really takes you from an input to an output and produces a correct output that meets the problem definition. But usually in problems, unlike data structures, you have an input, you have an output, like sorting was an example. In sorting, remember what was the objective. I give you an input, which is a bunch of n elements, and you are supposed to have an output where the elements are sorted. In the selection problem, I'm giving you n elements, I give you an index I, and you need to output an element whose rank is I. So these are problems. Here we are in a different realm, a different world, a different domain, where we have a concept of data structures. So in what way are they different? So in a data structure, we don't really have a notion of an input or an output. What we have is a structure which has no beginning and no termination. It only is supposed to satisfy a certain condition at every point in time. And we also attach to it a concept we call a query. So what is a query? A query is a question or a question with an action that you apply to the data structure, and you need to execute them efficiently. And unlike a problem where you have a beginning and an end, here the data structure keeps living, in principle, forever. So to those of you who are familiar with the concept of operating systems are not data structures, but they have a similar flavor where they don't have a beginning or an end. They are there forever. Hopefully the system will not collapse, but they are not supposed to have a termination. Or they don't start at a given point. You can hit them anywhere in the middle and they keep staying alive while giving you some guarantees. So here we have a notion of a max heap. So a max heap I already explained. It's where you have this relationship between a node and its parent. And now I'm going to demonstrate to you a form of a query. So what is a query? I'm giving you a max heap. Suppose it is valid and it's correct. And again, it's a nearly a complete binary tree, which satisfies the max heap thing. And now I'm changing the value of one node. And how am I allowed to change it? In this example, only to a smaller value. So if I take a value of a node and I change it to a smaller value, what can go wrong? Clearly, if it was a legitimate max heap before, if the node had a value which was smaller than its parent, it will still be smaller than its parent, right? So that's not a problem. We are not expecting any infringement of the max heap property as a result in that direction. But if the node had a child, one or more children, now, since we reduce the value of the node, we are not guaranteed anymore that the value of the node will be larger than or equal to both its children, if it has two children. So we need to do something about it, because we may need to change the value of a node, but we would like the whole heap to still maintain the max heap property. So what is the query in this case? The query is lowering value of a node, and now we need to accommodate this change so that the max heap property will be satisfied. And the procedure that we are going to learn is called max heapify. So heapify, we use the term heap to make it a verb, and max heapify will be the protocol that does that. And in order to simplify things, rather than going over the code of max heapify, I'm going to jump to an example, and you see that it's not really difficult. So here you have an example where before we had here, say, the value 15 instead for node I. Okay. So when we had the value 15, it was a perfectly max heap. But now I'm considering a situation where I lower the value. So suppose that I lower it in this example from 15 to 4. And now I need to apply max heapify. And the essence of max heapify is captured by this statement. It's percolate the new content down to a correct position, where upon determination of this percolation, so to speak, the element will reach a point and will be exchanging values with other values in the nearly complete binary tree, so that the max heap property will be satisfied again everywhere. So what is the basic idea? Very simple. I have here these two nodes, this value 4 and 2 children, 14 and 17. So let's ask ourselves, how can we bring peace to this new rift? Because 14 and 7 are both unhappy that they have a parent who is smaller. So the basic idea will be the following. Clearly, if I put 7 here, 14 will remain unsatisfied, right? But if I put 14 here and move 4 here, say, I at least made peace in this frontier. So this is exactly the idea. The idea is to look at both children and exchange, and in case one of them or more is larger than the new value at the parent, we exchange the one which is larger. So that's exactly what we see here. So 14 and 4 exchange their locations. And now we look again at both children of 4, which is now the parent of these 2 children. And now we see that only the 8 remains unhappy. And when only one is unhappy, it's easy to say it because then you just exchange them. And now the 8 moves here, the 4 here. And it should be clear to you that by following this step, we will be able to fully satisfy again the max heap property by doing no more than order of age operations, where age is the height, number of edges from the location that we performed the change originally all the way to a root, to a leaf, I'm sorry, in its subtree. Because we do one operation here, one operation for this at this level, and then we reach a leaf. And when we reach a leaf, obviously, we are done. So that's the notion of max heapify. And to be frank, it's written here in a pretty awkward way, which it's not illegitimate. I have no criticism on the detail here, because that's what programming is all about. But it's much but as I explained it, I hope it's much simpler. Because there is nothing more in terms of ideas than what I told you. And I hope that you all remember that the one thing that the book does this shortcuts, if you will, is by using the notion of exchange AI and AI largest. So it's the exchange that is happening here between this and this, for example. And I hope you remember that maybe in another book, the exchange will not be written as exchange, but rather take AI, put it in an auxiliary location, copy A largest into AI, and then copy the auxiliary location into A largest. So the book sometimes picks this shortcut, sometimes they do not. But it's not really a criticism, I'm just making a point that if you try to write anything in the most detailed fashion needed, there is almost no limit to it, because then the question is why not to write in assembly code and so on. So the only thing I'm trying to say here is that you need to be aware of this code and how things are written using elementary programming steps, but we are going, as we advance in the course, to speak using higher and higher levels of abstraction. But we need to always remember that when it comes to complexity, this is the type of level of complexity that we need to always reason about. And this will become even clearer when you get the programming assignment later in this course. Okay, so I hope that the notion of max heapify is clear, and its complexity is proportional to the height in which you did you applied it, the node to which you applied it. And I also hope that you remember why we have here really a notion of maintaining a heap, where you start with a legitimate heap, you have a query, which is a change of value, and now you incorporate it. And at the end of this process, you again have a legitimate max heap. And observe that we didn't solve any problem, right? We just had a data structure, we applied a query to it, and at the end, we again have the same data structure, in a legitimate data structure that fits the definition of the data structure. Okay. So now we are going to approach now the question of how to start making use of it and how to actually build a max heap from an array of value. So now you are given an array A. Like, imagine that we are given an array of 10 elements, but the elements are not sorted, because here they are already satisfy the max heap property. Imagine that they are not sorted. How can I take 10 elements which are unsorted and in a pretty efficient way store them in a max heap so that each element will appear exactly once here? So I'll need to permute them somehow. And now we are learning an efficient way of doing this, of how to take, in this case, 10 elements given in any order in the original array and transform them into something which is a legitimate heap satisfying the max heap property. And the idea is actually very simple. So unlike my style elsewhere, I'm going, because the code is so short, I'm going to review the code, directly and then demonstrate it on an example. Okay, so here is what we do. So we need to build a heap for an array A of a given length. And the idea will be to start with a concept of the least significant parent in the nearly complete binary tree. Okay, I know that this is a mouthful. The least significant parent in the nearly complete binary tree. And we are going to start sorting things from leaf level, or from the lowest level, lowest parent, all the way to the root, and somehow things will fall into place. Okay, so I realize that what I said now is not very clear. I'm going to demonstrate it in this example. Okay. If you look at this nearly binary tree of 10 nodes, and suppose that the original array you give me is this messed up array. Of course, it's not sorted, it's just whatever arbitrary values you get on an array of size 10. So where do I start? So look at what we have in this array. We have leaves, and then we start having parents. Among these parents, the parent which is in the least significant location, if you will, is, remember what's going on with the values of the leaves. You start with leaf at location 10, which is the highest. All of these are leaves. There will be some point as you start going up or down in the values here, where you hit a node who is not a leaf anymore. What is the first node which is not a leaf anymore as I move here from 10 to 9 to 7 to 6? It's the node indexed 5. Now, why am I insisting on starting with this node? The reason is that when I start with the lowest parents, it will be easy to handle them, because the only thing I need to handle here is a situation where we have a parent and one child. Or it can be two children, but both children are guaranteed to be, in the beginning, to be leaves. So to the extent that there is an infringement of the max heap property, it will be very local. So it is convenient for me to start with the lower nodes and then move all the way to the root by going through the levels, these guys and these guys, and finally the root. So by going from leaf towards root, I'm ironing out the problems one at a time. And when I reach the next level, I'm likely to have a single infringement. So if I have a single infringement, it's easier on me. So let's see what's going on here. Here at this stage, no infringement, right? Because we have 16 and 7, so no problem. Then I move to this node, to this parent right here. And just to clarify, observe that node 5 fits here a condition of length A was 10, divided by 2 floor. Length A was 10, divided by 2 is 5. So I start this iteration with the value 5, and I do max heapify on the node at this location, which is location 5. So this tells me start here. What will be the next node that this code is telling me to go to? I started at 5. I have to go down to 1. So after 5 comes 4. After 5 comes 4. So where is 4? 4 is here. So I go to 4 and I look at the value 2. It has 2 children, 8 and 14. Both are unhappy that they have a parent whose value is lower than them. What is the algorithm for max heapify? You exchange the value of this with the largest among them. And for that reason, following the second step, step B, 14 moves here. What will be the next node that we will consider? It will be node 3, right? Remember, we started at 5, now next week 4, now 3. At node 3, we still have only 2 children, both are leaves. And the 2 children are 10 and 9. Both are unhappy that their parent is a 3. 10 is larger, so the 10 will move here. Next, we move to node 2. We finished with node 3, we move to node 2. Node 2 is a new animal in the sense that now node 2 has underneath it a more involved structure, not only leaves, but actually a subtree, or it has grandchildren. Up to now, nodes had only children, not grandchildren. So now we look at what's going on here, and we resolve the relationship between node 2, that has a value of 1, and its children using the max heapify, but we do it max heapify all the way similar to how we saw max heapify before. So now we apply max heapify recursively because 14 and 16 are unhappy with having 3 a lower value. 16 is higher, so 16 will replace it, but once we bring 3 to here, the 7 will be unhappy. So the 3 will migrate all the way to the leaf, and 7 will be here. So just think what you can expect. You have 16 here, 7 here, and 3 here. And that's exactly what you see in this figure right here. And finally, we reach node 1. In node 1, we have 4 at the root, and we have 2 children which are unhappy, and 10. And now we apply max heapify to that, and the max heapify for 4 actually pushes it all the way to here. Why is this valid? Because 16 and 10 compete for this location. 16 wins, 4 moves here. 14 and 7 compete. Both are unhappy with the 4 here. 14 wins. 14 moves here. And now we have 8 and 2. 8 wins and 4 moves here. So we have now 8, 14, 16, and 4 here, which is the final situation. Okay, so this is really the way in which we build now a fully legitimate max heap using max heapify. So you see max heapify, which is a recursive procedure where when we apply it using this routine of build max heap, gave us an arbitrary order in the array and produced at the end a legitimate max heap. So I hope that it is clear to all of you that this is a correct procedure. If you have a question about the correctness, why is this correct, that's the time to raise it, because to raise your questions. Because the next question that I will focus on will be the complexity analysis, which, as you will see, can become quite elegant here. But is it clear to you that by applying this procedure of build heap by recursive calls to max heap, which in max heapify, I got originally a messed up array, and I ended up with an array that fully satisfies the max heap property. Is this clear to everybody? If you have questions about that, about the correctness, that's the time to raise. Okay, so I'm going to assume that you understand the correctness of this and you are convinced that it's correct. And now the question is, what is the complexity of this? And what you see on the margins of this slide, you will see a bunch of different ways of reasoning about the complexity, which I'm going to skip, not because they are not important, but because they are, I would call them non-native computer science and engineering, in the sense that they apply the type of summations that you have seen in many courses before in your life on the math side or wherever. What I wanted to demonstrate to you is how to reason about the complexity of build max heap using a completely different way of reasoning, which I would guess that either nobody has seen in this class or very few have seen before. And the technique is known by the term amortized analysis. So what is my objective? I can tell you right now, my objective is to show that the total number of operations of build heap or build max heap is linear. And observe that this cannot be true if I were to argue that for each max heapify, I do only a constant number of operations, because if this was the case, this would be trivial. But because clearly, when I did the last step here, and of course, imagine that we have a general n, the number of operations for the max heapify for the root can easily be logarithmic, right? Because this would be the height of a tree if you have n nodes. And if this is the case, then clearly you cannot argue that each application of max heapify is a constant. So we need to do something more sophisticated. The amortized analysis shows us a pretty elegant way of reasoning about it, which is known by the name amortized analysis. So what is really the idea behind amortized analysis? The idea, or the big idea at the highest level of abstraction, is that while I cannot tell you that each max heapify will cost me a constant time, I show you a way of arguing about the total number of max heapify by way of actually charging the bank for each operation I do. And in the beginning, I credit my bank account with a certain number of dollars, and I charge each operation by $1, if you will. And what I prove at the end is that I remain with a positive balance. So if I put in my account $N and I do whatever number of operations, and I show that my balance at the end is non-negative, what have I established? That the total number of steps I've done is no more than N. And that's really the idea. So how are we going to do it? So please follow me and see how it's done here, which I think is pretty elegant. Okay. So each time that we apply a call of the max hippify primitive, of the hippify primitive, not the max hippify primitive, the hippify primitive, which we do the local change between a node and its children, we charge the node at which the call is initiated, not where the basic step is applied. I'm going to make a point to it, $1. So let me explain. The last round here, if I initiate it here, and it takes me 3 steps to get from here to the root, as I explained, from the root to the node, because I apply hippify this ways and this ways and this way, I charge $3 to this node, to the root. Okay, so that's the important thing. Don't charge it locally, charge it to where the max hippify was initiated. Okay, so that's the idea. So let's see how we are going to do that. So, in the beginning, we put $2 at each of the n/2, or n/2 minus 1, non-leaf nodes of the tree. Okay, so in this example, we take the 5 non-leaf nodes of the tree, 1, 2, 3, 4, and 5, and we put $2 near each of them. We put no money near nodes 6 to 10 because they are leaves. How many dollars did we put? At most $n, right? Because we have n/2, at most n/2 non-leaf nodes, and we put $2 by each. Now we are going to revisit the algorithm, but this time we care basically only about the charging scheme of what will ensue. So in the inductive step, we assume that upon completing a hippify at a node of height h, a total of h dollars remain at that node. Okay, so the new assumption is that upon finishing hippify at a node, I remain with a balance of h dollars. So just to be sure that we understand what the inductive assumption is, if we go back to this node, it means that this node 5 starts with $2. Because its height is 1, the inductive hypothesis will mean that when we are done, it remains with a single dollar. This is, again, its height is 1, so when we are done, it remains with $2, with $1, I'm sorry. For this node, the inductive hypothesis will mean that when we are done, it remains with $2. Why? Because its height is 2. And when this is done, it remains with $3 because its height is 3. There is a path of length 3 from this node to a leaf. Okay, so this is the inductive hypothesis. And in a way, you can argue that the inductive hypothesis holds in a trivial way for the leaves, because the leaves are of height 0, and when you are done with them, because you never start, you have h dollars because h is 0. So that's a trivial base for the induction. Okay. Now I'm going to prove to you that if we are making this inductive step, and the inductive hypothesis should be clear, right? I finished nodes of height h. I'm now treating nodes of height h plus 1. So if I can show you that going into step, into a node, into a hippify step for a node of height h plus 1, the inductive hypothesis allows me to assume the following. that the node of height h+1 had $2 in the beginning, right? And then the inductive hypothesis tells me that because if it is of height h+1, each of its children, which are already finished, have a balance of age. Okay? And because of that, think about what will happen next. When you do heapify to this node, you go all the way to a leaf. And when you go to a leaf, how many steps do? You do 8 steps. So you have a total balance at the node of height h+1 of 2h plus 2. And now you are at liberty to use h+1 out of them in order to charge all the operations you do at this level. So how many will remain? h+1, which is exactly the inductive claim. Is the proof clear? Now, to remind you why this completes what I'm trying to establish here. Because I started with a positive, with an n dollars, and I remain with a positive balance, which means that the total number of operations I've done is no more than n. Does this make sense to everybody? Okay, so this is really a native computer science argument called amortized analysis. And the reason that I went through it is that it is used in pretty advanced algorithms. And what I like about this example is that this is the simplest example known to me where we can apply this native computer science reasoning to an algorithm and show that it actually gives a pretty strict bound, which I think is pretty cool. Okay, so if you have any questions about this, that's the time to ask. Okay, I'm not getting any questions today, so I'm going to continue. No questions? Okay. So the one thing I wanted to now connect this to sorting. So how do I sort? The idea will be quite simple. You give me a bunch of elements, an array. What will be the first thing that I do? I do a max heap. So now I have all the elements arranged in a heap that satisfies the max heap property. We have seen that, right? So this step should be clear. Here comes the new element. The new element is the following. I want this element sorted. What does it mean? I want them in an array will be in an increasing order. So take the first the element at the root. What can you tell me about the element in the root? It's the maximum, right? So I pick this element and I do the following trick. And once you understand this trick, you will immediately see why this is so the sorting problem. I take this element and I put it at the rightmost location of the array. And now I declare that the heap size came down by 1, which essentially means that what I did is that, this example, I take this 16, I put it here, okay? And upon putting it here, by declaring that the heap is smaller by 1, what happened to the connection of this node to its parent? It disappeared. I chopped it off. Okay, it's as if I apply scissor here. And I took this leaf and no more, the leaf is not part of the tree anymore. So what happened to the tree right here? It is a tree which has only 9 nodes. And what was the trick? The trick was to replace 1 and 16, put 16 here, chop it off, and now apply, because 1 will be here, apply the max simplify in a way that should clearly put the 14 here and put the 1 back here, because that's, we have seen this before. So what will happen next? I will take the guy who is now at the top, put it in this location, put the 1 here, apply max simplify, chop it off from the tree. So now I have 2 leaves which are connected from the tree, and that's it. How much did the first step cost me? We already reasoned this will cost me linear time. Each of the current operations cost me an extra logarithmic time. And for that reason, we got an n log n algorithm. Is that clear? Okay, so I'm going to quickly revisit this when we meet again Monday. And I will also try and remind me, if I don't do that, to upload the next the next batch of slides, because we are almost done with this chapter. Okay, any questions for today? No questions? Okay, if there are no questions, I'm going to end the class here, and we'll see you Monday. Okay, bye.